are the quantum vacuum oscillations theoretical, or are they real or not? They've moved past that, and they're developing methodologies and technologies to actively harness the energy of the intrinsic energy of the vacuum and the intrinsic entanglement. So Eduardo Martinez has done a lot of work on developing protocols for entanglement harvesting. So he calls himself a space-time engineer, and I think that's an apt moniker. He's a space-time engineer. And his research team have presented the first experimental activation of strong local passive states and the first empirical demonstration of quantum energy teleportation as originally proposed by Hota. So their experiment confirms for the first time the establishment of entanglement in the ground state of a multipartite quantum system, and performing the local operation in classical communication protocol allows for the activation of localized zero-point energy density without energy transfer through the entire system, so obviating that SLP restriction. The energy can be accessed freely and instantaneously via the intrinsic entanglement of the field, essentially a teleportation of the physical quantity of energy of the quantum system. And here it is reported just last March. So the experiment performed by Eduardo Martinez and his fellow researchers used a nuclear magnetic resonance to induce quantum entanglement between carbon atoms and an organic polymer molecule. When the organic polymer molecule is specifically resonated with magnetic fields and radio pulses from the nuclear magnetic resonance device, the researchers were able to induce the ground state of the atoms in the molecule to become quantum entangled. This mimics the intrinsic state of spatial correlation in the entanglement nexus of the quantum vacuum. So if we recall that depiction of Alice and Bob, that was depicting very specifically them accessing in a very natural way the quantum vacuum energy density and its entanglement network. In this experiment, they're kind of artificially inducing replicating that quantum vacuum entanglement via the ground state, inducing the atoms, the carbon atoms in this molecule to go into the ground state. That's their vacuum state. A finely tuned series of radio pulses from the nuclear magnetic resonance device entangles the ground state of the carbon atoms. And we've got A for Alice and B for Bob. The intermediary carbon atom, AN, could then function kind of metaphorically as a messenger between A and B. So this is your classical communication channel by analogy. And transfer the entanglement state of A to AN via resonance transfer with a secondary radio pulse and a final pulse aimed at B and the intermediary atom AN simultaneously to transmit the information of the excited ground state of A to B, enabling B, our carbon atom C3 here, to access the excited ground state of A via the non-local entanglement network, breaking the SLP state, strong local passivity, and releasing energy from B. So the researchers, with these finely tuned radio pulses, the timing is pretty critical in this experiment, they induced the system into the vacuum state, the ground state of the polymer. Everything becomes quantum entangled at the vacuum state, the ground state. They have a second pulse that sends the information of the entanglement state of A to AN, and then a final pulse that transfers that from AN to B. B essentially accesses the information of the entanglement state of A, and that energy is released by B. The researchers recorded the release of that energy from B and demonstrated that the energy was quantum mechanically teleported between the two carbon atoms in the polymer. So, it was like a simulation in a organic molecule, in a polymer, and you could extrapolate out where, okay, A and B aren't carbon atoms in a resonance chain of a molecule, but are two people like Alice and Bob. And instead of the ground state of the molecule, they could use the vacuum state of the quantum vacuum. And so via this experiment, it's very possible that we could develop technologies that teleport energy quantum mechanically. And this has some very interesting applications and implications. But note that this is more like a simulation of vacuum entanglement, where the ground state of the carbon atoms is playing the role of the quantum vacuum that naturally contains spatial correlation for all systems. In this case, the entanglement is being induced. That is entanglement harvesting by bringing the carbon atoms to the ground state. However, in future experiments, it should be possible to run the experiment in intrinsically quantum entangled systems, in which the entanglement does not have to be induced, but is present via the naturally occurring spatial correlation of the quantum vacuum energy density. And Masahiro Hota has said that that's what he would like to see next, the next step on that. Now, this was only one of the experiments, but to me, it's one of the more exciting ones. There was a secondary experiment performed by a researcher, a physicist named Ikeda, who was actually a student of Hota's. And he was able to demonstrate the same kind of quantum energy teleportation using quantum computers, IBM, free use, publicly available quantum computers. And so the details of that are available in the article that this review is based on. But as can be seen here, after repeated measurements, the researchers reported an average decrease in the energy of carbon atom B. Goes down here. There's a higher energy value, and then as the protocol is repeated, the energy value of B goes down as energy is being released. So that's like drawing energy from the system. You're accessing, harnessing that energy. This has important implications for multipartite quantum systems, like the qubit systems in the quantum computer, because this is a potential mechanism to draw energy from them to keep them super cooled. So cooling, keep them in a quantum entangled state using this protocol. So this could have direct applications in increasing the robustness and efficiency of quantum computers. Now, while it would normally take almost 700 milliseconds for the energy to travel via normal dispersion from A to B along this polymer molecule, the researchers showed that with the QET, quantum energy teleportation protocol, it took no longer than 37 milliseconds for the entire energy transfer process. So that's about 20 times faster than the classical case scenario of energy propagation, along the molecule. So